Well, I hope you're ready to tackle some big bears. We're revving up for the AP Calculus exam, and I know these free response questions can be scary, but I know you've got what it takes. And I tell you what, you keep working, keep plugging away, and before you know it, you're going to be dancing in the streets celebrating that 5 that you earned on that exam. You're going to knock your parents' socks right off. And be sure to stick around to the end of the video here today. We're going to talk about and go over maybe one of the most popular topics that shows up year after year on the exam and show you a few ninja tricks there at the end. So without further ado, let's dive into question number 2 from 2019. This is a great question for both AB and BC students. And let's see. So our theme today is motion along the x-axis. And so we were describing particle P, and we've been given his velocity in the form of this table. Now, tables can be very dangerous. They can lead you into false bear traps. And one of the things you want to watch out for is making assumptions that a typical function might behave like. So for instance, you'll notice from x equals 2.8 until t equals 4, the velocity is positive here and positive here. So example, one assumption is to assume that the velocity is always positive, within that time frame right there. But that would be a dangerous assumption to make. We have no guarantee that would be true. In fact, the potential does exist that the velocity is negative multiple times within that interval from 2.8 to 4. Now, jumping into part A here, the language right out of the gate suggests that we might be dealing with one of those pesky theorems like the Intermediate Value Theorem or the Mean Value Theorem. Why there must be at least one time. That is making me think of a theorem. And in this case, we're trying to prove the existence of a V prime value. So what you'll notice is we've been given velocity values and we want to prove the existence of V prime. That to me is screaming mean value theorem. It's really easy to get those theorems confused. And if you have trouble separating and distinguishing when to use which one, I'm going to type in a little blurb right here in a second that is worth putting in your notebook. And I guarantee it's going to help you decide which theorem to use and when. So here's how I separate the theorems in my head. If I'm using V of t values to prove the existence of a V prime value, then it's mean value theorem, because really what we're doing is we're analyzing the slope of V. But if you're just using V to prove the existence of another V value, then you're going to use intermediate value theorem. So for instance, within this interval right here, you could prove that the velocity had to be 50 at some point, as it progresses from 55 to 48, but that's not the case. So we're going to go mean value theorem. And first of all, those prerequisites are that the function V has to be both differentiable and continuous. So we want to make a statement of that. So, and a lot of times I'll set it up like this. They said V was differentiable right here. So the fact that V is differentiable implies that V, if you're not used to using this little arrow right here for implies, I'd really encourage you to add that to your toolbox. V is continuous on that closed interval from 0.3 to 2.8. Okay, now what we're going to do, you'll notice if I apply the slope formula between these 2 points, I'm going to end up getting 0. So I said that, the velocity at 2.8 minus the velocity at 0.3 divided by 2.8 minus 3, or 0.3, is basically 55 minus 55 over 2.5, which is going to make 0. And therefore, by the mean value theorem, there must exist a value C. And then we're going to sandwich it. Now notice this is going to be an open interval. That's another little bear trap that a lot of people don't get. This is a closed interval up here, but this one that I'm writing right now is going to be an open interval such that V prime, and I should include that little subscript of P like they're including it, of C is equal to 0. Boom. All right, in part B, we're going to try to approximate the value of this definite integral using a trapezoidal sum. And so in other words, just like any definite integral, we're trying to approximate the area underneath that curve, and we're going to use the area of our trapezoids to create that approximation. Now, quick review here. Our trapezoids are oriented a little differently than they were probably back in, your old geometry classes. They're going to be oriented kind of tall and upright like this. And so if we consider these as your height 1 and height 2, you've got your base here. The general area is going to be 1/2 then the quantity h sub 1 plus h sub 2 times your base. So that's kind of the format you're going to see me use as I go through these. So peeking at this table, and I'll scroll up here real quick just in case you don't have this question in front of you otherwise. So let's see here real quick. So the very first trapezoid is going to have heights of 0 and 55. Those are the two numbers I'll add together. And then their base is going to be 0.3 units. Now the second trapezoid is going to have heights of 55 and negative 29 with a base of 1.4 units. Notice how I subtracted the 0.3 from the 1.7. And then that third trapezoid is going to have heights of negative 29 and 55 and a base of 1.1 units. So that gives you a little overview of what my setup's going to look like. All right, so here's my setup, and I tried to color code the three different trapezoidal setups, and I actually want to highlight one thing that's a common mistake. I'm going to erase something here. See this little equal sign that I put? Let's see if I can erase that. That should really be an approximation sign. And in writing this part right here is not mandatory, but I really like it because it helps me to not lose sight of exactly what this integral is, or these trapezoids are approximating. Plugging that in all into my calculator, I got 40.75 meters. And that is a measurement describing displacement. In other words, over this time interval, the particle traveled to the right, then he traveled to the left, and then he traveled to the right. And when it's all said and done, he was 40.7 meters away from his starting point. All right, diving into part C here, we're introduced to a second particle, or a second race car, and the velocity function is given by this equation. So we've kind of got a table describing the velocity of particle P. Now we've got an equation that's describing the velocity of particle Q. And they said, find the time interval during which the velocity of particle Q is at least 60 meters. So in order to accomplish that, I'm going to graph this function right here over the window from 0 to 4. And then I'm also going to graph 60 and basically see when that velocity graph is above 60. So you're probably doing this on your TI-84 or something equivalent to that. I'm going to shimmy on over to Desmos. And let's see if this was going to work. All right. Maybe. All right. So what we've got cooking here is this turquoise graph right here is the velocity of particle B, or Q, I think it was. And then I graphed a second, that dotted line right here represents just a straight line at 60. So I'm going to find this intersection right here to be about 1.866. We'll find this intersection over here to be about 3.19 or 519. And we're going to store those in our calculators. So we don't want to lose or round off any intermediate answers. Bingo. All right, so having those stored, and what kind of evidence would I show on my paper? Not a lot. I don't have to show too much. I'm basically going to indicate that I took this function, I set it equal to 60. The solutions were, let's see, I make sure, about 1.866 ... I stored that as alpha A. The second intersection, or the second solution, was 3.519 ... I stored that in B. And now they said, find the distance traveled. Now that could potentially be different than displacement. In this case, I don't think it's going to be, because it looked like that graph was strictly above the x-axis. And so the particle's traveling in one direction, and that's to the right. But anyway, anytime I do distance traveled, I'm going to put absolute values around that velocity function just to be safe. And it's just a habit that we've established. It can never hurt in a case like this to put them on there. And then we'll evaluate that on our calculator to get about 106. And here's where you can actually round. 106.109 meters is the total distance traveled by particle Q. Now, part D is where we're going to dip into that first fundamental theorem eventually. And that is absolutely a guaranteed concept that is on the exam year after year, and it comes in many different variations and forms with little twists and turns. But just to set the table here, now particle P, if you'll remember, from that opening paragraph, his initial position is at 0, the origin, so to speak. So here's P. Now Q starts way back here to the left at negative 90. So 90 units to the left of the origin is Q. And then pretend like you said, all right, racers, take your mark. On your mark, get set, go. And and they're off to the races. Now, Q is traveling strictly to the right because his function is always positive. Now, P, as you saw in that table, he does a little to the right, a little to the left, a little back to the right, so on. The question, what we ultimately want to decide is, how close are they to each other when we get to 2.8? In other words, we want to measure what is the displacement of each particle during the time period between t equals 0 and t equals 2.8. So here's how I'm thinking about this. Let's take a look at Q first. So what I'm thinking is, let's review this in a general sense. If you have a definite integral, and let's say you're integrating f prime, that's guaranteed to be equal to f of b minus f of a. And I think if you recall, the integral of any velocity function is going to be a position function, okay? So what I'm thinking is that if I integrate the velocity of q, and let's say we want to do it from 0 to 2.8, that's guaranteed to produce the position of q at 2.8 minus his position at 0. And now what you can do with that first fundamental theorem is you can kind of add and subtract terms from one side to the other and manipulate it a little bit. And basically what you're going to end up saying is that his position at 2.8 is equivalent to that initial position at 0 plus this integral. So, which makes total sense to me, because I'm thinking, okay, let's take his original starting position and then add on his accumulated displacement during that time period. So this is going to be negative 90. You could throw this definite integral into your calculator. You're going to get about 135-ish. Let's see. Let's go with 939-ish, ... Adding those together gives you about 45.937. 45.937. Okay. So he's done a lot of traveling. He's been moving. All right. Now let's do the same thing. Basically repeat that process, but we're going to do it for the other particle. So let's say the integral from 0 to 2.8 of the velocity of particle P is going to be the position at 2.8 minus the position at 0. Again, adding terms from one side to the other, we could say the position at 2.8 is really just the position at t equals 0 plus the displacement. I apologize for my handwriting is not the easiest to read here today, especially. Okay, now this value right here was 0 because he started at the origin. Now that displacement in this particular case was an approximation that we created from the trapezoidal sum that we did. So they said use your answer from part B. So that's where we're going to use that 40.75. So this equal sign right here is really an approximation sign because of that trapezoidal sum. Now the question is, they're pretty close to each other. We're going to subtract this answer from this answer. So they are about 5.188 meters apart from each other at t equals 2.8. All right, not too shabby. So if nothing else, continue to work on that first fundamental theorem. You're going to see it all over the exam. You're going to see it, I bet, more than once on the multiple choice section. You're going to see it at least once on the free response section. It's something to take to the bank. Ladies and gentlemen, I hope you found something that was helpful tonight. If so, please hit subscribe below, hit that like button, and share it with your friends. All right, have a great night.